Welcome back to Educator.com, Intermediate C++. Today, we have templates. Templates are a core feature for flexible code reuse. You say you write this wonderful algorithm and you get it all working, it's testing, and you use integers for it, and you think, well, you know what, I have another use for this, but I need to use doubles. Now, C++ is strongly typed. You can't just shove a double in there and expect it to act like a double. So, hey, solution, use a template. You define the template for an integer, you'll run it, you test it, it works. Hey, wonderful. You run the same code using a double, and it should work the same. So the code is compiled with whatever type or types that you give to the template. Your functions and classes can be reused without being rewritten, but retested. Make sure. So you don't need to cut and paste a function for each type, which can lead to errors. Say, okay, I've got the integer version of it, I've got the double version of it, I've got the string version of it, I've got the version for this type, the version for that type, etc., etc., etc. Then you say, well, we found a bug. Let's go fix something. So you go fix the integer version, you fix the double version. Somebody forgets to go fix the string version. Then the other versions, blah, 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 you don't have to worry about it. You've got one version, you fix that, and recompile it for each type that it needs to work with. And one of the nice things about it moves the emphasis away from objects and back into algorithms. In the olden times, the algorithm was most important. And with the development of object-oriented programming, objects became the all-important thing. Well, this brings it back down to the algorithm with whatever object you want to work with. As long as the algorithm is sound, then it should work with any object. There are other languages that are just now coming on board with this sort of thing. I won't mention Java's name, but they've been around for a long time. All your containers and various things had to have a generic object. And so you bring the object back out, and then you have to cast it to whatever type you happen to be using. Well, recently they've come on board with something that C++ has had for quite a while, where now you can have an actual container full of a particular type of object and not just a generic object that needs to be cast. So now you can create a linked list of integers or a linked list of whatever your defined class is. And when you pull the object out of that particular linked list or whatever the container happens to be, you don't have to cast it into your type. You already know that by the definition, this is your container full of this particular object that you want. So that's what template buys for you. We do have a downside. You can't hide your algorithms in a template. So templates tend to be used for types of things like linked lists and binary trees, where the algorithms are well known, they're well established, they've been published for decades. Nobody's got a copyright on these particular algorithms, but they're there and they're available for you to use. That defeats your encapsulation of your algorithm. You do have to be careful with the types used, because, and we'll see an example of this a little later on, make sure when you give it a type that every operation in that algorithm actually does apply to that type. So for example, you have a string type, you can't subtract strings from each other. It doesn't make sense in the world of a string type. Now you can add strings together, which is interpreted as concatenation. You can print them out, and there's various other things you can do with a string. But if you have a template with an algorithm that needs to subtract something, it's not going to work with a string type. Now you can also have multiple types in a template. So we'll have this template work on this type and do whatever they're going to do with those two types. You can have a default type, like in a function you can have a default parameter, where if the caller does not specify a particular type, it will use int, for example, as the type instead of whatever is not provided. And you can also give it non-type parameters, like you can give it 17, and it will use the 17 however it needs to be used in the template. You can specialize a template. So we can have the generic template that's used for all of these various different types, but if we pass in, say, a character type, we'll do something slightly different. That would be great for the example with strings, to subtract things together. So if someone passes in a string type, well, we'll do something different. Instead of subtracting, we'll do add, or you could say, well, let's interpret that as to mean that the second string, instead of being subtracted, will look in the string to see where the second string is and then remove it, just as an example. And you can also pass templates as a type to be used in another template, and we'll see examples of that. So let's go on to the next slide.